Welcome to my channel Tech for Novice, dedicated to technology-related information for novice in simplified language. We know infrared light is invisible, but we feel it, and thermography is based on it. We will explore infrared theory applicable to thermography in a simple way by avoiding complicated mathematical formulae in this video. Price of thermography cameras have come down to couple of $100 and therefore affordable for many people. Though we are living with infrared radiation, we hardly think about it. Infrared radiation is invisible light similar to visual light in many aspects, and therefore we may think visual cameras are not that much different from infrared cameras. This thinking is not that wrong until we consider thermography. This video, dealing with basic infrared theory, is the first part in Thermography Series. If you own or intend to own an IR camera, or you are just curious about thermography or interested in various technology, then you are in the right place. Let us learn thermography with this video designed for novice. Thermography is infrared thermal imaging with temperature measurement and analysis. Thermal imagers without temperature measurement are mainly used for night vision, security, and military applications. Infrared radiation was first discovered in 1800. Thermal imaging technology was developed in 1930s, but military started to use this technology only in the 1960s when the price started to come down. They were still bulky and expensive for general applications. Industrial and medical applications started in 1970s and 1980s as thermal cameras were more affordable. Uncooled microbolometer technology was developed in this period. Uncooled microbolometer technology made thermal cameras more compact and affordable in 1990s, though still expensive for general public. Price and size of thermal cameras are continuing downslide with faster rate since 2000. Thermal cameras are now available in pocket size and as smartphone accessories. Let us see some of the advantages of thermography. Thermography is a passive remote sensing technology which makes it safe to use in electrical, mechanical, and environmental hazards. Thermal pattern is qualitative and temperature measurement makes it quantitative. Can capture fast-moving targets and fast-changing thermal pattern with temperature measurement in real time. Another advantage is non-destructive test, NDT, as it doesn't affect target at all, unlike many tests that require destruction of samples or at least some changes. It is convenient to use even in total darkness. Contact thermometers absorb heat from the target, which decrease temperature of small objects, making the reading unreliable. You also need to wait, unlike thermography cameras. Here is an example of real-time temperature measurement. Please note how the temperatures of polygon, AR01, rectangle, AR02, line, LI01, and spot, SP01, change instantly as drop of hot water is passing. Benefits come from the advantages. Thermography is a predictive and preventive maintenance tool. No financial loss with frequent inspection of plants, as no shutdown is required. Frequent inspections lead to early detection of faulty equipment, allowing scheduled maintenance instead of emergency shutdown due to severe damage. Next, what is infrared radiation and how it was discovered? German-born British astronomer Sir William Herschel was experimenting with light in search of optical filters for his telescope to watch the sun without damaging his eyes. He measured the temperature of different colors of light scattered by a prism. He noticed that heating effect got stronger from the blue end of the spectrum to the red. The heating effect was even greater when he moved one of the thermometers beyond the visible red end. This is how he discovered invisible light in 1800. The invisible light beyond the red light is called infrared rays or infrared radiation, IR in short. Herschel's experiment concept that led to discovery of infrared radiation. Herschel discovered infrared ray, which humans have always been aware of, but it was not linked to electromagnetism until many years later. Let us have a brief introduction to electromagnetic spectrum to help us understand infrared radiation. The electromagnetic spectrum is the full range of electromagnetic radiation. It is divided into separate bands, with each band consisting of a range of wavelength or frequency. One side of the spectrum is gamma ray and X-ray with shortest wavelength, and another side is radio and microwave with longest wavelength. Ultraviolet, visual, and infrared are in between them. Shorter wavelength radiation has more energy level even within the same band. Now let us see which wavelength are in visual and infrared bands. Visual spectrum includes wavelength 380 nanometer to 750 nanometer. And infrared band includes 750 nanometer to 1 millimeter. Let us summarize what is infrared. Infrared is the energy band between the visible red and radio microwave bands in the electromagnetic spectrum. Infrared is invisible to human eyes. As mentioned earlier, IR includes wavelength from around 750 nanometers to 1 millimeter. Infrared obeys the laws of visible light with few exceptions, though it is different due to longer wavelength. All objects with temperature above absolute zero or minus 273.15 OC temperature radiate energy within the infrared band. Visible light is a narrow section of the electromagnetic spectrum between ultraviolet and infrared bands with wavelength from 380 nanometers, violet, to 750 nanometers, red. When white light is passing through a prism, it is deviated twice due to refraction effect. The different colors of light waves experience a different degree of deviation due to difference in wavelength. This is the reason for separation of white light into its 7 component colors. Knowledge of heat transfer is essential to understand thermography. We are going to review it briefly even though we already know it. Heat transfer is the energy exchanged between materials, transferring from higher temperature to lower temperature. Usual effect of this transfer is an increase in the temperature of the colder material and a decrease in the temperature of the hotter material due to energy gain and loss respectively. Heat energy is transferred in 3 different ways. Conduction requires contact, which needs solid materials. Convection requires fluid flow and therefore needs liquid or gas, and radiation requires transparent medium or no medium such as vacuum. Infrared radiation could be reflected, absorbed, or transmitted through objects like visual light. If an object partially reflects, absorbs, and transmits incident radiation, then incident radiation equals sum of reflected, absorbed, and transmitted components. It can be expressed mathematically: W equals alpha W plus gamma W plus tau W, where W is the total incident radiation, alpha W is the absorbed radiation, gamma W is the reflected radiation, and tau W is the transmitted radiation. Alpha, gamma, and tau are material properties of the object that determine ability for reflection, absorption, and transmission of this object. From our last equation, W equals alpha W plus gamma W plus tau W. Dividing both sides by W, we get the result alpha plus gamma plus tau equals 1, which means sum of absorptivity, reflectance, and transmittance equals 1. According to Kirchhoff's law of thermal radiation, emissivity equals absorptivity. Emissivity is denoted by Greek letter epsilon. Now we can rewrite the equation epsilon plus gamma plus tau equals 1. If the object is opaque, then transmittance tau equals 0. Therefore, our equation for opaque objects becomes epsilon plus gamma equals 1, or epsilon equals 1 minus gamma. If the object absorbs all incident radiation, then both gamma and tau are 0. Now the equation can be simplified as epsilon equals 1. That is, emissivity equals 1. An object whose emissivity equals 1 is called a blackbody. A blackbody is a theoretical object that absorbs all incident electromagnetic radiation. Objects with emissivity less than 1 is called gray body. Emissivity of a gray body is the ratio of the thermal radiation emitted from its surface to the radiation from a black body surface at the same temperature. Emissivity is a material surface property that determines IR radiation emission efficiency. It is expressed by a decimal fraction in comparison to blackbody. Higher the emissivity, higher the amount of heat energy emitted by an object at the same temperature. For an example, if an object emits 80% radiation compared to blackbody at the same temperature, then its emissivity equals 80 divided by 100 or 0.8. Let us do a simple experiment to find out how emissivity plays a role in heat transfer by radiation. If two metal blocks of the same material, shape and size, one shiny and another painted black, are both heated to 800 OC, which one is felt hotter from the same distance and angle? The answer is black block, as it has higher emissivity and therefore radiation emitted from it has higher intensity. Which block cools faster if both blocks are left in the same environment? Again, the answer is black block, as it loses energy faster than shiny block due to higher emissivity. Shiny objects act as heat insulators by reflecting incoming external radiation and keeping heat inside enclosure due to lower emission. Every object emits IR radiation. Does it mean very low temperature objects also emit IR radiation? Yes, all objects with temperature above absolute zero emits heat. Absolute zero temperature is 0 Kelvin or minus 273.15 degrees Celsius. Even lowest temperature on Mount Everest is well above 0 Kelvin. IR radiation emitted by an object is proportional to its temperature, though not linearly. Thermography uses this relation for temperature measurement. Radiation intensity emitted by different objects of the same temperature may not be equal due difference in emissivity. It complicates the temperature measurement. Next, how we see objects in different colors. An object may reflect and absorb components of light illuminating it. What we see is the reflected component and its color is the object color as we see. We see a white object as white as it reflects all components of white light. A red object is seen red as it reflects red component of light and absorbs the remaining components. An object absorbing all components of light looks black as no light is reflected. Color of an object is a reflected component or mixture of components of light illuminating it, not originated from the object itself. Infrared spectrum is outside the range of light signals that we can see and therefore has no color. White material in visual could be black in infrared. For an example, white paper is basically black in infrared since they absorb most of long-wave radiation. Non-reflecting object is black in visual concept. Color of an object is component of light reflected from it and absorbed components are no more visible. Both IR and visual radiation absorbed is emitted as IR radiation. If we assume reflected IR radiation is the color of the object reflecting it, then emitted radiation is also color of the object emitting it. Actually, reflected and emitted radiation are not distinguishable. Source of emission is internal energy of an object while source of reflection is other objects in front of it. Emission is proportional to the object temperature, though not linear, and reflection has no relation with temperature of the reflecting object. But reflected radiation mixes with emitted radiation, making the combined radiation intensity existing from an object no more proportional to its temperature. Therefore, we should try to avoid reflection. Transmittance of thermography targets is 0 as we consider only opaque objects for temperature measurement. Therefore, sum of emissivity and reflectance is 1. If emissivity is known, then reflectance is also known and vice versa. Emissivity is used to eliminate influence of reflected radiation for temperature calculation. Now let us see how infrared radiation is affected when passing through the atmosphere. When infrared radiation is passing through the atmosphere, its intensity is reduced due to absorption by various molecules existing in the air, mainly water vapor and carbon dioxide. Overall transmittance depends on wavelength, atmospheric condition, and distance. Infrared cameras should be built for the wavelength that has higher transmittance through the atmosphere. You can see two wider windows in the graph, one for shortwave 3 to 5 micrometer, and another for longwave 7 to 14 micrometer with transmittance better than visual bands. Therefore, most of the thermography cameras are built for either of these two wavelength bands. Infrared transmittance through atmosphere varies widely for different wavelength bands. Interestingly, wavelengths from 5 micrometer to 8 micrometer and some other narrower bands are absorbed almost completely. IR radiation emitted by higher temperature objects is mainly in shorter wavelength band, while lower temperature objects emit mainly in longer wavelength band. Therefore, shortwave has higher sensitivity at high temperature and longwave has higher sensitivity at normal temperature. Longwave has higher transmission through haze, fog, dust, and turbulence, while shortwave has higher transmission through high humidity. Thank you so much for watching. If you like this video, please comment, like, subscribe, and press the bell icon. Your comments with constructive suggestions will be highly appreciated.